So we wait a few seconds until people have joined. So maybe I start with my introduction, because then you don't have to wait so much. So I'd like to welcome all of you to this webinar on behalf of the European Microwave Association. My name is Jan Borowski. I'm with the University of Bochum in Germany, and I'm happy to be here today with Mark Lazzaro-Marti, who's from University of Rovira e Virgili. And yeah, I'll just share you some information. Yeah, our today's webinar will be on backscattering communications, advancing toward perpetual IoT operations. And before we start, so just to keep tension a bit high, we'll just to share a few slides about the series with you. Oops, sorry for that. That's first mistake. Oh. Wrong slide. So now oops, here we are. So, okay, as I said, I'd like to share a bit information about EuMA's activities. So we have this webinar series that you hopefully all know by now. There have been quite interesting webinars in the past as well, in addition to today, of course. And I'd like to give you the hint that these webinars are online available for you on the YouTube channel of the European Microwave Association, so you can just Google it and I'm sure you will find it, on diverse topics related to microwaves. Furthermore, I would like to just do some advertisement for this year's European Microwave Week, which is the premier microwave event in Europe, basically featuring 3 microwave-related conferences at the same time and place. The EuMIC, the European Microwave Integrated Circuits Conference, for those of you who are interested in microwave circuits, integrated circuits, the European Microwave Conference, and the European Radar Conference. And in addition to the technical program of these 3 conferences, we have quite a large industrial exhibition where you can network with industry and all the people there. There are schools for students and doctoral students, for example, the Microelectronics Design School and the Radar School. And there are, since a few years, there are novel, distinct young professional events and a career platform for those of you seeking job opportunities. Even though the deadline has just passed on 1st June, there is a volunteer program, and I think there's an opportunity to maybe just still get into the program. So that's why I'm showing you. So you have the opportunity to help us out with organizing the conference, doing some work during the conference and the exhibition. Not too much, but your benefits are that you get free access to all 3 conferences and the exhibitions on those days where you're not helping us out. Up to 7 nights in a local hostel, free lunch on your duty days, and the opportunity to visit all the students' events. So as said, the official deadline has passed, but I'm sure the portal or the email is still open. Okay, so now I come back to our webinar today. As said, I'm happy to have Mark here with me, who is giving us a talk on backscattering communications, advancing toward perpetual IoT operation. Mark was born in Tarragona, Spain in 1959. He received the bachelor degree and the master degree from Rovira e Virgili University in 2017 and 2018. He obtained his PhD also from there in 23, and he's a lecturer currently at the university where he teaches in the bachelor's degree in, sorry for background noise, in telecommunications engineering. His research interests include backscattering technologies, microwave circuits, and applications in the millimeter wave bands, amongst others. He was awarded the Young Engineers Prize in European Microwave Week 2023, where we met first, Mark, and received the first prize for best communication at the 3MT contest during the EuMA National Symposium in Spain. Yeah, Mark, I'm happy to have you here. I'll just quit my mic and the shutters are done today. And yeah, I'm looking forward to your talk. Thanks for being with us here.
Yes, thank you very much for the introduction, Jan. Give me 1 second to share the screen. So I think that now you can see the presentation. So I will start. Well, this presentation will be a kind of introduction to backscattering communications. So it's really a pleasure to participate in this webinar. And basically, the structure of the presentation will be this one. I will start defining what is backscatter. Probably most of you that have a good technical background in engineering microwave will already know it, but for some students that maybe can have access to this webinar and it's something new for them, I will try to define it and put the context here. Then I will talk about the basic concepts on backscattering communication. So what is the theoretical basis? So what are the bases of a modulated tag and how we can see it in frequency with the very simple measurements. And then I will present an application that we published recently in 2025, where we use a LoRa backscattering system to try to improve a commercial application that we already have. And it's basically a home surveillance system based on LoRa backscatter. So what is backscatter? Well, actually, the term backscatter was, we use it with the discoverment of radar. So basically, it refers to the term of transmitting an electromagnetic field. And when this electromagnetic field interacts with an object, it scatters back to the direction of the source, a reflection. And this is what we know as the backscatter field. So actually, despite that backscatter refers going back to the source, in modern backscattering communications, it's not necessarily have to be like this. So all the technologies that work studying or trying to get information from that reflections, studying the modulation in the backscatter field, I think that can be considered backscatter communications or backscatter technologies. So I would like to start a little bit with this timeline. Obviously, this timeline is based on the evolution of backscattering technology. So here, obviously, we have the main backscatter based technologies that are radar and RFID. And obviously, we have many other milestones in the history, like the discoverment of electromagnetic fields, the discoverment of the vacuum tube by Fleming, or the development of the transistor. But I would like to go directly to mention few dates here. That is basically, I think that the first one is that I have to start when talking about backscatter communications is Heinrich Hertz. In 1885 to 1889, he was the first one doing some experiments with radio links that he observed that doing experiments with reflectors, something was happening there. And actually what was happening was the consequence of the reflection of that electromagnetic field and that backscatter fields. So after that, we obviously, in the context of the First World War, we were developing the wireless communication with Marconi, Popov, and I think that the first backscatter-based application is the radar. And then I have to mention Christian Holzmeier, who in 1904 presented the first system to detect objects that detect objects, and it was application for detect in the naval field. And basically, it was the predecessor of what we know nowadays as a radar. That later on, due to the applications in the First World War, they developed very fast the radar due to the huge potential in order to detect planes, trucks, ships. So the radar, as it knows nowadays, was basically presented by Robert Watson Batt in 1935. And then after that, I have to talk of the second main technology based on backscatter, that is radio frequency identification. And the predecessor of the chips, the RFID tags, as we know it nowadays, I think it was designed by Leon Thermin, that basically, again, for military applications in the Cold War, they developed a kind of RFID tag that was fully passive. So that's why it's considered the predecessor of RFID tags. And from that point is that we started to work in what we know nowadays as RFID. So I would like to mention also the work of Harry Stockman in 48, communication by means of reflected power, and the work of Harrington theory of low-data scatters in 1964, because they put the pillars for what it will be, what will become the RFID. And obviously, as RFID apparently had no military applications, the development delayed 20 years, and it was not until the end of the 20th century that we had millions of RFIDs spread around the world. So after that, basically, we have these two major technologies based on backscatter, and we are now in the model research on backscattering communications, and we are working on several challenges on dealing to unlink a little bit backscatter communication from radar and RFID. And as I will talk in the next slide, we will talk a little bit about where we want to reach or what are the challenges that we are trying to solve. So I always like to start with this little figure where you can see the power consumption as a function of the range of the main wireless technologies, right? So basically here nowadays we are using Wi-Fi, Z-Wave, Zigbee, LoRaWAN, cellular communications, Bluetooth, and what we have in common, all these technologies, is that we use conventional radios to establish the point-to-point wireless communication. So that's true that with these technologies, we can reach ranges of 10, hundreds of even kilometers of range, but normally the power consumption, as we use traditional radios, we need power amplifiers, we need local oscillators, and then normally the power consumption in those technologies that, for example, consume less power, like Bluetooth Low Energy, we are talking in the range of several milliamperes or tens of milliamperes. So in the other side, we have those technologies based on backscatter fields. And for example, we have RFID and NFC. And the advantage is that we are not generating that signal locally. So we are only reflected, like in RFID. NFC, that's true that its magnetic coupling is near field. In contrast to RFID, there is far field. But I think that I can consider both of them in the backscatter bucket. And the advantage of using backscatter is that now the power consumption is on the range of microampere. So what we need here, we can see in this plot that we have clearly a gap of we need a wireless technology that provides a solution for those technologies that requires tens and hundreds of meters of communication range, but we need the power consumption in the microampere range. And this is basically what the model research in backscatter communication is trying to do. So what is the milestone? I put here in this slide, the milestone is perpetual operation, but this is something more related to marketing than perpetual operation is something utopic. Nothing is perpetual in this life, but we want to tend in that direction, right? We want, I think that IoT nowadays have been corrupted a little bit. And one of the reasons is for marketing purposes. Nowadays, worldwide, we have, I think, if I remember correctly, 7 billion devices connected. So with a population of 8 billion, we are talking about two connected devices for each people. So for each person. So even probably thinking now how many devices I have in my house, it's probably higher that value. But I think that the number of connected devices is growing exponentially, and we need a change in the paradigm in order to overcome that wall that we have in IoT. It's what I say that marketing that IoT is corrupted. It's because nowadays we are trying to put electronics everywhere, add new functionalities, new connectivity, add smart sensors in domotics, in smart cities. And the idea is that I think that the essence of IoT is be invisible for the user. The IoT should be something like the ABS of the car. So it should be there, and when it have to work, it works, but you don't have to be worried about configuring it or changing batteries or things like that. Any kind of maintenance is required by the ABS of the car. And IoT should be something like this. So make no sense trying to add humidity sensors in plants, temperature sensors in rooms, if we try to solve a problem that we really didn't have, but we had more problems because we have to be aware of replacing batteries. We have to fabricate a lot of batteries for all those devices that is growing exponentially. We have to be aware if we lose a communication. So that's why I think that in IoT, we need to change in the paradigm, and we need to decrease the power consumption. And I think that backscatter communications have the potential to reach that point. So what are the challenges that we have nowadays in backscatter communications? I think that as any other wireless communication, we have always the trade-off between power consumption, data rate, and communication range. So always when we want to increase the communication range, we have to increase the data rate, we have to increase the power consumption. So we are always tailoring this trade-off for each application. So in backscatter communications, it's not different. We have to deal with problems like complexity, cost, privacy, security, compatibility, and well, scalability. And I think one of the most important is energy efficiency. But to mention three, I think that three of these challenges that also were mentioned, some of them in a paper published by Joshua Smith in et al. And at 2020 or 2021, where they talk about where are the challenges that we have in backscatter communications. And the first one is basically unlink backscatter communications from short range operation. And this is linked to RFID. RFID normally use radio frequency energy harvesting to have completely passive tags, and these radio frequency energy harvesting normally have these circuits have a sensitivity of -80, -30 dBm. So it makes no sense having these energy harvesting doing a bottleneck in our system when our receiver is capable to demodulate signals, for example, in LoRa at -130, 140 dBms. So actually unlink this or remove these radio frequency energy harvesting from backscattering systems will allow us to unlink it from short range application and be capable to basically reach large communication links. The second thing that I think that it's a challenge and we have to tend in that direction in backscatter systems is avoid using a dedicated carrier wave. So normally in a backscattering system, we have the transmitter, we have the tag or the target, and we have the receiver. So the idea is that at some point, ideally, there are a lot of works that propose doing that and prove that we can do that, but it's complex. We have several problems to deal with. But the idea is be capable to use the signals that we have in the environment and piggyback information there from our tag to send it to the receiver. So with this system, we avoid the necessity to deploy carriers and having data transmitter continuously emitting a carrier wave. So we use, for example, the TV radios, we use the Wi-Fi modems that we have at our homes or anywhere. And for example, the smartphones can transmit the carrier wave, And I think that it's one of the challenges that we have to reach to 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 reach the new generation of backscatter communications. And finally, I think that the last one, but not less important, actually the other way around, I think it's the most important, is the regulation. Regulation standardization is mandatory to start seeing commercial application based on backscatter communications. We have enough research. There is a lot of contributions in the literature. We have proved a lot of proof of concepts, applications that can work with backscattering communications, but we cannot see commercial applications rather than RFID. We cannot see IoT application based on backscatter communication. And this is, I think that the main reason is because we don't have regulation on that kind of communication. So we have to stipulate what is the kind of carrier that we have to use. We have to stipulate what is the modulation, what is the duty cycle that we can use, and standardize a little bit what are the different parameters that have to use the spectrum. Maybe we need a dedicated spectrum for that kind of systems. And if we don't do this regulation, I think that we will never start seeing this technology in commercial applications. So, okay, so now let's talk about the basic concepts of backscattering systems. So I will start with this architecture. This is the typical architecture of a backscatter system, the architecture of a radar, the architecture of an RFID system, and it's a monostatic architecture. So the principle is very simple. We just transmit electromagnetic field, and we have two options. In radar, normally we do not modulate that signal. That's true that yes, in some cases we modulate it, but the basic concept of radar is try to steal information from the target. So we send electromagnetic field, and as a function of the shape, the material, the dimension, the speed of the target, the reflected signal will have a specific property. So the physical parameters of that signal will be modified, and we can process that signal to try to steal or get information. So as a function of the amplitude, the phase, the frequency. On the other side, we have, for example, RFID transponder. And the difference is that normally in modulated tags, the tag is trying to send information to the transceiver. That can be radar, or in RFID systems can be the reader. So in this case, basically, by modulating the antenna, by loading the antenna with different impedances, basically we generate digital information, or we encode digital information, and then the reader is who gets this information, the identifier, temperature sensor, humidity sensor, and basically process it and save it. So always, I think that in research, we always try to classify systems. It is a kind of thing that we like to do, and I think that the classification is complex because always depends on the criteria of the person that is doing the classification. But I think that a good classification in backscatter systems is as a function of the architecture of the system. So, for example, in this case, we have two main groups as a function of if the system is monostatic or bistatic, and in each group have its own advantages and disadvantages. So in monostatic backscatter communication systems, we have technologies like RFID and radar, as I showed in the previous slide. And in bistatic backscatter communication systems are those systems where the transmitter and the receiver are not collocated in the same place. So we can put it in different locations, and we have several advantages over the monostatic, also disadvantage. So inside this bistatic backscatter communication system, we can distinguish two subgroups. The first one is those that do not require a dedicated transmitter. So we use ambient signals that we can find there, and we try to reflect those signals, adding information. So those are the ambient carrier backscatter systems. And then those systems that have a bistatic configuration, but we are deploying a dedicated transmitter to establish that communication. And these are known as the dedicated carrier backscatter systems. So what are the advantage of monostatic architectures compared to bistatic architectures? In the monostatic architecture, we have a problem is that we have the transmitter and the receiver in the same place. So normally we have a self-interference of the transmitter over the receiver. So this is sometimes called the doubly near-far problem. The transmitter is transmitting a strong signal, and the receiver have to adjust the gain to be able to not saturate the low noise amplifier of the receiver, and this obviously affects the distance that we can reach in this configuration. Another thing to mention that is a disadvantage of the monostatic compared to bistatic is the worst case link budget. So when we calculate the link budget, the worst case is when the tag is in the middle distance between the transmitter and the receiver. So in that middle distance is where we have the worst case link budget. And in monostatic configuration, this is always the case. So the tag is always at the same distance than the transceiver. So this in bistatic configuration, it's not necessarily this. This is not necessarily the case. So normally in bistatic configuration, we have the transmitter in one place, receiver in one place. The tag is in movement in the middle, but normally when we move the tag, we go closer to the transmitter, closer to the receiver, and it's not necessarily the worst case link budget. So normally we are in a better situation compared to monostatic architectures. Also, an advantage of bistatic architectures is the flexibility of the system. We can choose specifically the location of the transmitter to avoid multipath interferences, to deploy the system in challenging environments. And also there are papers that, very, very good papers that propose adding extra transmitters to increase the range of that specific bistatic system. To mention one advantage of monostatic architectures compared to bistatic architectures, monostatic normally the extracting or demodulating the codification of the tag over the carrier, it's simpler because as we have access to that transmitted signal, because we have the receiver and the transmitter co-located, it's easier to separate the carrier from the information modulated by the tag. In bistatic architectures, when we try to separate this information, the processing is more complex because we have to try to record the carrier in the receiver, but the path that the carrier follows from the transmitter to the receiver is different than the path that the carrier follows when it goes to the tag and then from the tag to the receiver. So normally there we have an offset, and the processing when we try to get information is much more complex. So let's talk about the basics concepts of modulated tags. So actually, this is very simple. The idea is that when we transmit an electromagnetic field, the power of the receiver can be calculated as with the radar equation that comes from the Friis equation, but considering the radar cross-section of that third element. So we have the transmitter, receiver, and the target or the tag. So in modulated tags, the idea is that we load the antenna with different impedances and we modulate the reflection coefficient. So in this case, we have two reflection coefficients, and the radar cross-section now have to be calculated as the differential radar cross-section. So actually, as we will see in two slides, I will talk about how different topologies that we can use trying to maximize the power at the receiver, playing with these reflection coefficients, but commonly used technique is using an open circuit and short circuit to get a reflection coefficient of 1 and minus 1. So we get a 2 in that modulus, and we can basically maximize the differential radar cross-section. So how we can encode information with this simple backscattering front end? The idea is that depending on the load that we connect to the antenna, we will modulate the amplitude or the phase of the signal that we reflect. And depending as the frequency that we use to modulate the tags, so the frequency that we use to switch between the antennas, we will modulate the frequency of the reflected electromagnetic field. And this is interesting because by modulating at a frequency high enough than the bandwidth of the carrier, we can separate that reflected signal from the carrier and then make it easier for the receiver to demodulate that information. So this is a very simple method to increase the signal to noise ratio and facilitate the work to establish that communication and consequently increase the range of the backscatter communication. So just the last thing that I want to mention here is that when we switch instantaneously from one impedance to the other, at the end, we can model this system with a square wave. So we basically this effect of switching between the two impedances is modeled as a square wave, and we can develop that square wave with an infinite summation of sinusoids. And if we are using a 50% duty cycle, we will get the odd frequencies and we will get all the harmonics at the odd frequencies, and are those harmonics what we use to encode information of the reflected packet. So this is basically defined, it can be defined in the frequency domain or in the time domain by the equations that we have at the bottom of this slide, and the amplitude of the harmonics only depends on the coefficients of these Fourier series. So a very rapid measurement that we all can do in the laboratory, transmitting a frequency tone, modulate the reflection coefficient of the antenna at a constant frequency, for example, 100 kilohertz on the left-hand side. And you can see that as we're using a 50% duty cycle, we get all the harmonics of the square wave. And this is basically what we want, separate the transmitted signal from the carrier wave to increase the signal to noise ratio and increase the communication range. And on the right-hand side, you can see the same case, but with a frequency modulation of 300 kilohertz. So in the case of use and spread the spectrum carrier wave, we can always increase the modulation frequency to separate that signal from the carrier wave. So now let's talk about common topologies that we can use when we design the tag. I think that I will present two topologies. There are more topologies, but one topology is using passive loads. So we for example, here you can see the reflection coefficients in the Smith chart. And the case that I mentioned is that one that we load the antenna with a short circuit and an open circuit, and we maximize the differential radar cross-section. So we maximize the power at the receiver of that signal. What is the problem is that in this topology, that is the B topology, where you can see the antipole stage in the Smith chart, we are not harvesting energy. So we increase the communication range, but to power up this radio frequency front end, we need a battery, or we need another energy harvesting system different than the radio frequency harvesting system. So this is the difference between the topology of the case A, where basically in one state we use an impedance that is reflected, in the other case we use an impedance or a harvesting circuit that is absorptive. So it's matched. In this case, I wrote 50 ohms, but it's not necessarily have to be 50 ohms. The only idea is that we absorb all the signal and we try to rectify and get a DC signal, power up the IC, and basically bias the front end automatically without the need to use batteries. So what is the second option that we can use? Use active loads. What happens if with passive loads we have requirements that are not accomplished, so we need an extra range? So then we have the option to use a reflection amplifier, and this is something that when I will talk about the application that we presented, we integrated a reflection amplifier. So this is also this is a non-topology that was presented in 2014 by Quimionis et al. So I will talk a little bit more about that, and I will recap a little bit about what I presented in 2023 in Berlin. But the idea is that we can connect the antenna to the reflection amplifier, so have an amplification and overcome that limitation of the unitary circle. And we have two options. The first one, by biasing or not biasing the amplifier, we can modulate two states, and this is enough to backscatter the signal, to reflect the signal. Maybe if we design correctly the front end with more power compared to the passive loads. However, if with this system is not enough, then we can go for the option B, that is basically having the reflection amplifier always on and use a phase shift modulator. So the idea is that the phase shift modulator have a direct line and a delay line. The delay line introduces a 90 degrees phase shift, and as the signal have to travel twice through this modulator, we will get an out of phase of 180 degrees between the two states, and we will maximize the differential radar cross-section, leveraging the gain of the reflection amplifier in both states. And you can see in the Smith chart, the reflection coefficient, what I'm talking about in the plots A and B. So okay, so now that we have introduced the basic concepts on backscatter communications, let's talk about the application that we presented recently. That is basically a home surveillance system based on LoRa backscattering. So the idea it was because maybe some of you have one of those. Nowadays, there were a lot of interest in a commercial system that is a home surveillance system that is very simple. We can all buy one of those. And I personally buy one of those, so you can install it in your house. And the idea is that it's just a receiver with a set of sensors that we can install it at the entry points, at windows of a home, a warehouse, an office. And the principle of the system is very simple. We are using sensors that are wireless, that are powered with a battery, and when the sensor is triggered, we send an alarm or a signal via AM to the gateway, and this one activates the alarm or sends the SMS or whatever. So the idea that was here is, why not implement this system with backscatter communication using LoRa backscattering? And we basically did all the work to prove that this can be done with backscattering with a more efficient front end. And the goal was to replace the battery on those sensors that we have installed in windows and doors. So basically, we did the implementation of the tag, and we proposed all the communication based on backscatter, based on LoRa, and we proposed a modulation, as we will see in the next slide, to try to not send binary information 1 or 0. If it's 1, we trigger the alarm. If it's 0, not everything is okay. Try to codify more information, but what is the modulation that we have to use for this? So before going to the next slide, just one thing, that is commercial systems normally use an AM modulation. We bought one of those sensors and we tried, and the AM modulation have a power consumption. It's a narrowband modulation, have a power consumption of several milliamperes. So the first thing that we did is implement the system with LoRa. LoRa is a spread spectrum modulation based on CSS. So we have a very high processing gain. It natively, it's more robust to interference, have orthogonality. So it's a better option when we try to think in a home surveillance systems that can be susceptible to jamming attacks. So the other reason to use LoRa, obviously, is that with backscattering is a very good combination because LoRa have a very high processing gain. So basically the demodulator correlate the incoming LoRa signal and multiply it by down chirps, the up chirps by down chirps, and we get a frequency tone with a very high processing gain. And this very high processing gain helps us to compensate for the double path loss that we have with backscatter communications. So what is the modulation that we propose here? What we thought is that, well, we can try to send information in a digital way. So for example, using an on-off key modulation or modulation the modulating the amplitude, the phase, the frequency, we can try to send an identifier so we can distinguish which of the sensors trigger the alarm. But the thing is that there is a more optimal solution, and basically that was what we tried to search for, and it's basically an analog modulation. So we talked about the different properties that are inherent in LoRa receivers, and one of the properties is the ability to compensate for frequency deviations. So this means that the LoRa receiver, when receive a packet, it can basically compensate for time deviations and frequency deviations. So it can also demodulate, and it can provide natively without modification to the user with that deviation from the central frequency of the channel. So we thought, well, so we have the LoRa transmission in the middle, and we are reflecting in the sidebands those LoRa packets. What happens if we modulate each of the tag with a specific modulating frequency, and we introduce a unique deviation frequency, a very tiny deviation frequency, unique for each of the sensors. So that was the modulation that we chose for this application, basically for two reasons. The first one is because it's faster than a digital modulation. So then we optimize the power consumption of the tag. So we spend less energy on that communication. And the second reason was that if we are trying to implement a surveillance system, the idea is how much time it takes to send the information, more time that the system can be jumped. So as fast as we go, the more secure that it will be. So basically, this is what we did. We decided to introduce this artificial frequency deviation, and in the receiver, when we detected, we have previously saved in a database the deviation of each of the tag, and we can distinguish which was the point that triggered the alarm. So with this configuration, we can go up to 625 sensors. Optimizing the spectrum, we only need one receiver placed at one of the sidebands. So we don't need to have several receivers and modulating at several LoRa channels. With only one channel, we can demodulate up to 625 sensors. And what I will, in the next slide, there is one problem that we had to deal with in order to implement this modulation. And it's basically the frequency drift of the oscillator of the transmitter and the receiver. As I mentioned, LoRa have the ability to compensate for frequency drift, and this implies that they do not require a very precise oscillator. So we have a considerable frequency drift that basically go against the modulation that we are proposing. Because if we try to introduce a specific frequency drift to distinguish each of the tags, and the carrier signal have the oscillator have a frequency drift higher than that gap that we are using, then we will fail on determining what is the tag that is sending the alarm. So basically, hopefully, the new family of LoRa transceivers here already integrated a temperature compensated oscillator, and that was basically what we needed to develop the proof of concept of this application. So here, this is just a measurement of the old families of LoRa transceivers, the SX1270 something. The X at the end depends on the band that we are operating as a function if we operate in Asia, Europe, or United States. And for the new family, the SX1260 something, we can see that we got a frequency drift up to 52 hertz. In comparison to the old family, we got almost 1K kilohertz of frequency drift. So there is actually we always have the option to compensate manually for that frequency drift. So if we are working with the old family of transceivers and we want to have a more stable transmission or try to compensate for that drift of the carrier, we can always integrate a temperature sensor. So with a previous calibration, measure it, make the regression, and compensate each time that we transmit a packet, try to compensate it as a function of the temperature. So So basically, that's it. So now let's talk about the implementation of the tag. So in this case, for the implementation of the tag, we went for the topology of the reflection amplifier with phase modulator, that it was not a novel topology, it was a non-topology. So let's see first the design of the reflection amplifier. The reflection amplifier is not something really new. Actually, the topology to design one of these amplifiers is the topology of an oscillator. So the idea is that we can use any of the typical topologies, the Colpitts, the Clapp, the Hartley, to basically design it. And we only need to operate close to the unstable region, but carefully biasing or carefully designing to not go to the unstable region. So to recap a little bit what I presented in 2023, I talk about integrated that kind of amplifiers in backscattering tags. So the problem of the reflection amplifier is that when I fabricated the amplifier in the laboratory, I observed that as a function of the input power, when I characterize it and I worked with it, as a function of the input power, the behavior of the reflection amplifier changed. So the problem is that when the input power increase a lot, the reflection amplifier can start oscillating, and in that situation the power consumption of this amplifier increase a lot. We basically amplify the noise floor. We can generate interferences in near bands to where we are operating, and this is basically what we don't want when we are thinking in a system with hundreds of tags, and tags that can be in movement and can go closer to the transmission source. So they can start oscillate, and basically it will be impossible to establish a communication there. So what we proposed in the European was to basically control the system by control the amplifier by enabling or disabling the amplifier only by monitoring the current consumption of the reflection amplifier of the transistor. So we only need to put a shunt resistor and a current sensor IC. In that case, in the European Microwave Conference, I implemented the current sensor with two operational amplifiers, but we can directly go for a current sensing IC. So with this way, when we go closer to the transmitter, we can disable the reflection amplifier. That is basically what we want, because when we are close to the source, it is basically when we don't need to amplify. And when we go away from the source is when we can activate the reflection amplifier. So with this very simple system, we cope with that problem that I observed in the laboratory. And then maybe the question that you will have is, why not to use that control system here in this application? And the reason is basically because in this application, we don't have that problem. In this application, we install the sensors in all the windows, entry points, doors, but the sensor will be static in one specific point. So in the moment that we go to install the backscattering tag, we can check if we need the amplifier, if we don't need the amplifier, and then enable or disable the tag. But the tag will not be in movement. It will never go closer to the carrier signal. It will be static in one point. So it makes no sense adding this controlled circuitry to the tag, because we really increase the final price of the tag unnecessarily. So in this case, actually in the European 2023, I used a Colpitts topology. In this case, I used a common emitter topology with a negative feedback, with using in the feedback branch, using a P network to filter the frequencies that I want to amplify. And at the bottom of this slide, you can see the characterization of the amplifier. So you can see how the gain decrease as the input power increase, because well, it's the gain compression of the amplifier, and obviously we go to the saturation point of the transistor. We can see also the gain of the amplifier as a function of the biasing voltage, that we tune it or we tailor it to get the maximum gain at 1.8 volts. That is normally the typical biasing voltage that we can use for the other ICs that we are using in the tag. And this is important when we try to design tags efficiently, because if all the components operates at a different biasing voltage, basically we need to use regulators. We need to convert that voltages or decrease the voltage or increase the voltage, and then we are losing power there. And it goes against the purpose of all of this, that it's always trying to be the most efficient as possible. And finally, on the left-hand side, we can see the current consumption of the transistor as a function of the biasing voltage. At the end, at 1.8 volts, we got more or less 22.3 dBs with a current consumption of 322 microamperes. So the phase modulator, for the phase modulator, basically we use the topology presented by Quiñones in 2014. So it was basically two radio frequency switch, one connected with a direct line and the other one connected with a delay line. So delay line of 90 degrees in order to get that 180 degrees out of phase states in the reflection coefficients. And for the delay line, that's right, that we can use transmission lines or discrete components. At this frequency, we decided to go for discrete components because then the modulator is not as bulky as if we use a transmission line. And that's true that at this frequency, we still have an insertion loss acceptable to decide to go for discrete components instead of a microstrip line or a coplanar guide. So here in the characterization of the phase modulator, you can see that we got more or less 2.43 and 3 dBs of insertion loss for both the states, the direct line and the delay line, and a phase difference between the two states of 84.28 degrees, very close to the 90 degrees that we need. The last part of the tag basically was, this was a little bit what battery you have to use. The idea is not to use battery. And by battery, I mean using a supercapacitor instead of a lithium polymer battery. So here, basically what we did is we had several supercapacitors in the laboratory and we checked which one of these had the lowest leakage current. So we want to avoid using lithium polymer battery because its fabrication, it's not the most sustainable process. So we wanted to go for a supercapacitor, but we can see here that the typical supercapacitor have a leakage current high enough to make it impractical for this application, because we have to consider that we're harvesting energy during the day with a tiny solar cell, and we have to be able to maintain that energy during the night period. And if we think maybe in Spain that we have a lot of light, a lot of hours of light during the day, maybe it can be okay with one of those capacitors. But if we think in other countries, in Europe, more in Europe, more in the north, for example, or for example, if we think in Iceland, the nighttime can be very large, so we have to ensure that our supercapacitor is capable to keep the voltage for long periods of no energy harvesting. So basically here we decided to went for the CAPEX prismatic capacitor that had a leakage current very similar to the lithium polymer battery. And the advantage of the supercapacitor is that the number of charge and discharge cycles, it's much higher compared to the charge and discharge cycles of a lithium polymer battery. So this goes or alignates with our idea to go for a tag that can operate for several decades. And just to have values of what is the operation time of our system with this supercapacitor. Basically in active mode, when we have the amplifier turned on, it lasts 28 minutes to lose, or it can be 88 minutes in active mode. If we have in active mode, but without the reflection amplifier, we can be 5-hour transmitting or backscattering packets. And in the sleep mode, the tag can hold energy for 48 hours. So it's more than the double of what we need to ensure that the system is capable to operate during night times. So here you can see an image of the tag. This is a render made with Altium. And on the left-hand side, you can see a breakdown of the tag power consumption and a breakdown of the tag components cost. And more or less, the power consumption is around 360 microamperes. And the cost of the tag is around $13 to $15 or euros. Always, we have to consider that this depends on the manufacturing, the price of manufacturing the PCB, the number of units that we buy for each of the components, but the price is more or less around 10, 12, 15 euros. So some measurements that we perform in the laboratory. Here you can see on the right-hand side, you can see the measurement of the reflection amplifier when we are transmitting, when we are backscattering LoRa packets in the sidebands, when the reflection amplifier is on, and you can see how the power reach almost minus 90 dBms, sorry, there is an error there. And when the reflection amplifier is off, we can see in blue how the amplitude of the reflected power of the backscatter signal is much less compared to the other case. So we also test the reflection amplifier in distance. So we put the transmitter at 3 or 4 meters from the tag, and we move the receiver away. And we can see how with the reflection amplifier on, we can reach almost 90 meters, and with the reflection amplifier off, we can reach more or less close to 60 meters. So here you can see how we have a boost in the communication range consequence of the integration of this amplifier. I have to say that at the cuts that you can see where we do not receive signals in the RSSI over distance figure is basically because we did the experiments in a real environment, in a hallway with a lot of metallic zones. We had a right whale in the right, and actually it was a very challenging environment with a lot of interferences, and it was a real environment. We can do the measurements in direct line of sight in rural areas, trying to avoid interferences, and I'm very sure that the range will be considerably higher compared to that one that we have here. However, I have to say that I'm not a super fan of trying to measure the maximum range of a backscattering system, because I'm a little bit skeptic about if this is really what or it's a measurement with significance over comparing this work over other works, because I think that it's very difficult to compare the systems as a function of the maximum communication range, basically for several reasons. It's not the same. We have a lot of parameters that we can use when we try to get the maximum range. For example, we can do these measurements in direct line of sight, in rural area. We can, for example, use directive antennas. We can use more power. In some countries, the regulations allows us to use more power compared to others. So we can use more power. So we can use, for example, tricky measurements, or for example, placing the tag very close to the transmitter and moving the receiver away. That's one thing that, yeah, I can measure the maximum distance of the system this way, but it's not the final case. It will not operate like that. The backscattering system always will have the transmitter and the receiver static in one specific point, and the backscatter will be in movement in that zone. So normally it's more fair to try to measure the maximum distance of a system in a specific area, but actually this area highly depends on the environment that we are trying the system. So this is a measurement that is very approximate. And on the other side, on the right-hand side, you can see some measurements that we did. This is a home surveillance systems. What we wanted is to check that we can still demodulate the backscatter packet, the backscatter LoRa packet over interferences of wideband interferences. So in this case, we used a signal generator transmitting a QPSK modulation. And we can observe that we can still demodulate the packets with a carrier to interface ratio of minus 12, minus 13%. Minus 12, minus 13 dB, sorry. But actually, this property is something more related to the modulation that we're using that related to a backscatter system. So LoRa have this ability to demodulate signals under the noise floor. So in this case, we proved that we can this match with the ability to LoRa to be demodulated under the noise floor. And finally, to finish, we wanted to test the system in a real environment. So we went to the flat and we placed the transmitter and the receiver 4.5 meters away, and we put the sensor at each of the windows of that household, of that flat. And we basically did a table for different transmission powers. And we basically here, it's very clear that the integration of the reflection amplifier is justified. So in many of the points of the flat, in many of the windows where we put the sensor, we can receive the backscatter packets without the need of the reflection amplifier. But in some cases, this is not the case. And it can be due to multipath interferences, or maybe because the distance is high enough to not reach that point. So in those cases, having the reflection amplifier and just having a switch to turn it on and off allows us to give to the system that extra boost and to be capable to basically reach all the points of a normal house. And additionally, this system, it's very configurable, so we can add more transmitters, more receivers, so we can actually adjust very well the configuration of the system, the parameters. We can play with parameters of LoRa, the spreading factor, the bandwidth, trying to increase and tailoring the system to the requirements of each environment, each office, each house, each warehouse, whatever. So I think that this is everything. Hope you enjoyed this little webinar of introducing the backscattering communications. And if anybody have any question, it will be really a pleasure to answer it.
Yeah, Mark, thank you for this very interesting talk. As said, there is an opportunity to ask your questions. There's a Q&A panel at the bottom of your Zoom interface where you should be able to write them down. And Mark, I'm not sure if you can see them there as well. So there are already 3 questions. I think some have been answered in the meantime already from your slides, but maybe we can just recap them. Maybe I just read them to all of you, and you can then answer.
Yeah.
Hi, many thanks for the talk and the slides. What might be the challenges to develop a backscatter tag in the high frequency bands, such as terahertz bands, for example? Oh, that's ambitious.
Yes, yes. Actually, at the millimeter wave band or a terahertz band, I'm starting now trying to scaling the systems to the millimeter wave band. So I have no experience in terahertz band. And I think that there is much more complex, and manufacturing is much more complex. Little errors in the manufacturing of the tags implies a huge frequency drifts. But actually, I think that I have not the expertise to say what is the challenges at those frequency bands. I think that the communication range of backscattering systems normally is limited by the double path loss. And at those frequencies, everything becomes much more complex. So I know that some signals can be absorbed even more by the environment at those frequencies. So I think that everything will be more complex. I would like maybe in few years, if I have the opportunity to scale or do some experiments in those frequencies, it would be nice to discuss it.
Okay, so my shuttles here again. I hope they do not disrupt too much. Next one would be, could you elaborate more on the tag circuit to produce the different frequencies from the transmitted tone? I guess that's the amplitude modulation, right? Maybe you can spend a few words on why there are several additional tones now coming out of the tech.
Okay, can you? I missed the middle of the question.
Oh, sorry. Can you please elaborate more on the tag circuit to produce the different frequencies from the transmitted one? So when you look at your on-off keying, why are there more harmonics there?
Yeah. Oh, wait a minute. Basically, when we receive the carrier in our tag, only by switching between the two impedances, actually we generate those harmonics. So we normally use the first harmonic because it's the one with the strongest power, and it's there where we place the receiver, and it's there where we try to demodulate information. So only by switching at the frequency higher or lower is that we can increase the frequency or modulate the frequency. So when we want to encode our information, when we want to modulate our backscatter signal in frequency, amplitude, or phase, if we want in frequency, we only have two modulating frequencies in the tag. So if we modulate at, for example, 1 kilohertz, and we modulate also at 2 kilohertz, we can encode information in those two states. So we have two states of frequencies, and the backscatter signal will have the frequency of the carrier plus minus the frequency of modulation of the tag. So I'm not sure if this answers the question, if I understood correctly what the audience was asking.
Yeah, and yeah, due to your let's say on-off modulation, you also produce the harmonics at twice the frequency as well, right?
Yes.
Yeah. Okay. So
Yeah.
I guess that's the question. Okay, and then the last question was regarding your voltage source on slide 18. If it makes sense to replace it by a harvesting circuit, and I think it makes sense that you have shown us that you did replace the power source by this capacitor, right? Which was very interesting.
In the slide 18?
Yeah.
Yeah, replacing the voltage source by the supercapacitor?
Yeah. Yeah, so the question was if you could replace the voltage source by some harvester, and I think on the next slide you have shown that you did so, and that this works good.
Yeah.
So
Yes.
the question was
actually
written down before you came to that point.
Yeah, actually, I think that one research line that complement very well the backscattering systems is the energy harvesting system. So all the circuits to try to harvest energy from any kind of source, it's fantastic to reach that milestone of the perpetual operation. So actually, due to my acknowledgement in this field, because I don't have a lot of acknowledgement in energy harvesting systems, I decided to go for the typical the solar energy harvesting, that I think that's the one with the best efficiency. But I think that there are many other options that can complement, that can help us to harvest energy to power up this backscattering front end. And yeah, I think that the idea is always try to remove LiPo batteries from those tags and go for supercapacitors for the lifespan that these devices have compared to LiPo batteries.
Okay, just to be sure, maybe I missed it. So in your current design, you now have a photovoltaic cell that powers the capacitor, right? But you could possibly also power it by some, I don't know, microwave harvester, just having like an energy harvesting receiver in some of the cellular bands, for example.
Yes, actually we can, but the problem is that using radio frequency energy harvesting, normally those circuits have a sensitivity close to between -80, -10, -30 dBms. And the sensitivity of that energy harvesting circuit limits a lot the communication range of the system. So when we go beyond that range, the problem is that we cannot harvest energy, and then the system is limited to a very short distance. So that's why we tried to not use the radio frequency energy harvesting system that it's the typical used in RFID.
Okay, but so you could build your harvester, for example, at some cellular network frequency, so I don't know, 800, 900 megahertz, and still operate your modulator in your LoRa.
Yeah.
Okay.
Yeah, this is a possibility, yes.
Okay.
Mhm.
And then I have a question myself.
Yes.
So you showed us nicely that you built this discrete network to realize the phase delay.
Yes.
To realize the 180-degree phase difference. Could you also include more than these two phase states to use some higher modulation and some higher order PSK modulation, for example? So like a 4 PSK or an 8 PSK to.
Yeah, you can. And this is something that some researchers in the literature did. So actually, you can create modulations much more complex, so modulators much more complex with a lot of states, and you can create the typical modulations like QAM or QPSK modulation. So it's something that have done in the literature.
Okay. Yeah. So I think that's it for today. Mark, I'm very glad you've shown us your interesting results, and was a pleasure listening to you. Yeah, I hope this holds for the audience as well, but I think so. Yeah, thanks for being with us. Thanks for bringing this webinar today, and yeah, have a good afternoon.
Same, thank you. Thank you very much for everything.
Okay, yeah, thank you to the audience for joining us as well, and bye-bye.
Bye.
Okay, maybe I